Welcome to 3Mac. Do you want to learn about computational design, advanced manufacturing, materials modeling, or integrity assessment? Then this is the channel for you. I regularly upload new content, so please hit the subscribe button below for regular updates. Welcome to this week's video, and in today's video I will show you how to perform analysis of a steel pipeline repair using composite wraps. So again this is a case study which I have got from a subscriber, so I'm just helping the subscriber out to make him learn in a way how to do this kind of simulation. So what you have is you have a pipe with a volumetric defect, as you see here. What you do in real life is you put some kind of adhesive. In this case they use putty during the experiments, and then they wrap composite layers around it, as you see here. So this is the composite layer, and then this is the final assembly. And they wanted to see, okay, before the composite repair and having a composite wrap onto it, what was the burst pressure. So they measured that during the experiments, and then after putting everything, they again tried to find out what is the improvement in the test. And they wanted to see, okay, if we can predict this using VIII or not. So that's what I'm going to show you in today's tutorial. Come with you. And as you can see, what we have done is we have found an approximate value of the failure pressure here, and which is around 34 megapascals, 34 megapascals, and I think in their case it was 35 or 38 megapascals. So let's jump into the technical details of ABAQUS and see how we can do it there. So see you on the other side. Okay, so let's see how we can do that. Again, I'm not going to give you any dimensions since it was from someone else, so I'm just gonna keep it as abstract as possible, but obviously the main aim is to show you the whole process of simulating similar problems. So first thing is to create a wrap. In this case the wrap was a kind of a fiber reinforced composite which was wrapped around it and let it cure for some time. So I will come back to that, how I have provided the properties, but I'm modeling it as a shell. So what I did was I just went to the part, I created a 3D part, deformable, and I selected shell and then extrusion, right? And then when I extruded the shell, the circle, I got this kind of shell structure. So this is my composite. The next part is basically the pipe, and in this case I was provided the geometry, so I just again do the same. I extruded everything, and then to create the defect I found out, okay, what are the lengths and width of this thing and what is the depth of this volumetric defect, and I created these planes, and then I have cut that section away and then removed some material from it. Again, this tutorial, the purpose of this tutorial is not to teach you the 3D CAD modeling, so I hope you can manage that in any other software, and you can bring your model here as well. So you can go to file and you can import any part using any other CAD software. So you can import any SAT model. I normally prefer IGES or IGS format or STEP format because they are easily, you can manage a lot of things through that, but you can try other formats as well. So again, you can import the part or you can make it yourself if you're very familiar with ABAQUS CAD modeling. So this is my pipe with a volumetric defect, as you see here, and then the putty, and the putty has the same dimensions as the defect because they put the putty inside the defect, they fill the defect, and then they bonded that composite wrap on the top. Alright, for the material properties, which is the second step in the module, and again, if you're not familiar with how to define properties or what these modules look like, then I have a course on my YouTube channel which is shown on the top, so please have a look at that. Alright, for material properties, I have to define the material properties for each material. For composite, in this case I'm using the same properties as I have done before, and that is to define the elastic constant in all three directions because my fibers can be oriented in different directions, and also the Poisson's ratio along with the shear modulus. So again, I'm using the values which are provided by the user or subscriber and through that paper. You can also use material model with damage and everything, so you can machine damage type model, and again I have discussed that in the video on the top on the right hand side where I have discussed about the damage in modeling in composites in ABAQUS CAE. So these are the same properties there, so you can directly use those as well. by creating a material library, and you can bring it here. So you can create a material library through here, where you can see I have saved materials, and I can bring any material here which I have done from the other files. Okay, so I go back to the model so that you can see what's happening. Then for Putty, what I have done is, again, I have modeled it is elastic properties, and they have, in that paper, they have given the elastic properties of that Putty because they did some experimental test on that. So I'm using those properties here, which is Poisson's ratio and Young's modulus. Steel, very common material, many times I have shown in my tutorials, so I have used the elastic properties as Young's modulus and Poisson's ratio. While for plastic part, again, they have given the experimental stress strain curve, and I have taken out the plastic part of the stress strain curve, and I have defined it here, as I have done in my other tutorials for material model definition. So again, you can have a look at that video if you are not familiar with that. Alright, so once you have done that, now I need to create sections which then I can associate with each component. So I have created two sections here. One is section 1, and that is based on the steel properties because I have a steel material properties, while the section 2 will be for Putty, and I have used the Putty properties, right? And then I assign these sections. So for as you can see, for Putty I have done this, and you can see in this case I have used section 2 which has Putty properties. Similarly, if I go to pipe, then I will be able to see the pipe properties. So you see steel properties I have used for the pipe itself through the section. For the composite part, I have the material definition as I told you, which is composite, but I don't use the section, rather I use the layup thing. Okay, so for composite, again I go to the composite, and I have defined the layer for this composite. As you can see, what they did was they had layers of composite with different fiber orientation, and they had 6 plies in that case after wrapping around the pipe, and I have defined those 6 properties here. So I have 6 different orientations: 0, 90, 0, 90, 0, 90, and I'm using the composite properties which I just showed you before. So this is how I have defined with the orientation, which is 0, 90, 0, 90, as I told you before. So this is how I have associated all the properties. Then you go to the next module, which is assembly, and what I normally do, I just bring all these components here one by one. Okay, so that's what I'm doing here. Once I brought them, you see they are all displayed here. For example, if I bring this here, then it will be somewhere here. So what I had to do then, I had to use this translate function, and I had to move this part from here, and I can select this point from here. Let's say I want to match this point of this part with the defect, which has maybe this part here, somewhere here. So I can select that there, and then I can bring everything here, and I can align everything based on that. In this case, I already have done this exercise, and I have fitted everything, that is pipe, Putty, and the composite wrap. Alright, so I will remove this part from the assembly because I already have that, and I just wanted to show you how I have done it, so I brought it here again. So I will remove this part which is there, so delete. Alright, so this is how I have created my assembly with everything there. Then I go to the step. In the step module, again I created a static general step right after the initial, and that static general step, when I press create button, then I get this window here, and I'm giving a total time of 1, and it's a rate independent case, so you can live with whatever time you have. And then I give a large number of increments to avoid ABAQUS to stop if it come across some kind of divergence, or it increases the number of increments because of the convergence issues, and it should be able to run whatever it is. And then I'm giving the minimum initial and the maximum to be 0.1, so that at least I have 10 number of outputs from 0 to 1 in the total time. Rest of the stuff is all default. I'm not changing anything here. Alright, then I go to the interactions. In this case, as you can see, I have to define an interaction between the Putty and the pipe surface. So what I did was I went to the surfaces, and I created these surfaces first. So what you can do, since you have an assembly with everything and it's difficult to select the parts, what I normally do is I just go here and I say cells, for example, and I can select this cell, and then I say intersect. Right, so now I have Putty here, and I can just rotate, and I need to create an internal surface and an external surface, because external surface will be bonded with the wrap and internal surface is bonded with the pipe. And that's how I have created the Putty in an internal surface. So you can see it highlights that. And then I have done the same with Putty outer surface, which is the other side. Then I bring everything back. and then I do the same with the pipe. So I can select the pipe now. So if I go here, I can say select. So I have to create, sorry, I have selected only the wrong one. So I will just add everything back, and then I go back again. You can do it with the part as well, it's easier. So pipe intersect. Okay, so everything is gone now, and you have this. If you want to remove all this, you can also remove it from views and part display option, but I will just keep it for the time being. So but you can see I have created a lot of sections before I move forward to create this volumetric defect, and it's easier sometimes to do in SolidWorks or some other CAD softwares. So in this case, I have to create a surface which was interacting with the putty itself. So that's the defect surface, I think, as I remember correctly. And you see it's all the surfaces selected. So this whole surface will be bonded with the putty internal surface. Okay, so we remember that. Okay, so I close this. Oops, sorry, I shouldn't have closed that. So I go back here, surface manager. All right, so I bring everything back, and now I go to the third part, which is also, I mean, pipe has also a surface, because that will be bonded with the composite internal surface. So that's this surface, and you can see it's just the outer part of the pipe itself. All right, so that's what I have done here, and then I do the same for the composite. So if I add everything together, and then you can see I have a composite internal surface which will be bonded with the pipe and the putty itself. So that's the one common surface here. Okay, and that's shown here as well. So now once I have defined all the surfaces, then I don't have to worry when I select the interactions, because then I can select it from my names. So I go here, and you can see there are two ties constraints. One is between putty and the pipe, and the other one is between the pipe and putty surface with the composite wrap. So this is the interaction between the putty surface and the pipe, and you can see I selected the two surfaces, which is defect surface and putty internal surface. While the second one would be, you can see the surface between the pipe outer surface, which is along everything, and the putty and the composite wrap internal surface. Okay, so that's what we have done here. Here one thing I have to explain, because there are two parts here. So what I did was, if you look at the surfaces, I have created the pipe putty outer surface. So this is basically the surface which is combination of this whole surface of the pipe outer surface and also the outer surface of the putty. So when I select this, you see it highlights the whole thing. So this means when I define the interaction, I just select this surface and I interact it with the internal composite surface, and it works fine, at least for this case. All right, then I go to the loads, and loads are again coming from those experiments. I have made some idealization to change few things, but it remains very much the same. I don't see much differences. So I have fixed this in the 3 direction, as you see here, this surface, and on the other side also I'm fixing in the 3 direction, which is the longitudinal direction of the pipeline, while I'm fixing one end of this. So this is just to replicate, because in the real test they had an end cap here, they had an end cap there as well, and they had a pipe which was pressurizing the whole system, right? So that's what I have tried to do here, but again, this is just idealized one, and the best would be if you can have a end cap effect in both sides as well, which is not there right now, but still it gives you reasonable results. So again, this is my approach. You may not disagree with that. All right, so these are the boundary conditions which I already showed you. Then the pressure load, which is the internal surface load, and you can see I have applied a pressure of 50 megapascals. It's an extreme case, and I want to see at what pressure up to the 50 megapascal it really fails. So again, if you look at ASME section 8, part 4 or 5, I don't remember exactly, but section 8, which deals with FEA. Then once your elements start to localize strains and your solution starts to divert, that's the point you take it as a burst pressure or failure pressure in high pressure systems. So according to a ASME part A. So that's what I'm going to do here. Meshing wise, again, you can see I've selected a very fine mesh. This is my composite wrap, which has shell elements, and what I have done in this case is I have used S4R elements, which are 4 noded elements with only curved things. Similarly for the pipe, I have used again 3D stress elements, which are 3D 8R elements. So these are reduced integration elements, and I have tried to avoid my the tetrahedron elements and try to keep it more hexahedron elements or cubical elements. Alright, so these are also, you can see like this, and they are also, as you can see, C3D 8R, which are brick elements in ABAQUS terminology. Okay, so we are not using tet mesh here for any of the components, because that's why I have all these planes, because I have to divide it into smaller pieces. As you remember, if you look at the meshing tutorial which I have here, and which gave you some tips and tricks on how to make a mesh of using brick elements in ABAQUS rather than using tet. So the mesh is very fine in my opinion. Again, you can make it coarser on this side to increase the efficiency of the computation or reduce the computational time in simple terms. Alright, so now I created a job and then I submitted, and you can see it's submitted now. So I can go to my results and I can see how it looks like, and this is how it looks like. So you see it's failing somewhere here, and it is failing at around, so I have removed the try it or something most probably. So let's see if I can bring it back. So you see it's failing around 0.647. so if I can open my calculator here, and so 0.647 0.6427 times 50, so that gives me a value of around 32 megapascals, and I think they found a value of around 38 or something megapascals. And again, my boundary conditions are not actual in my opinion, and they could be further refined if you have time. So that's how it looks like, but again the failure is somewhere there. And what else you can do is you can go back to your model, you can copy the model again, and you can basically, so you go back here, just copy the model, and if I can do that and show copy model, and I can say model 1, and you can say pipe only, right? And now if I go back to my pipe only model here, so what I can do is I can go back to my assembly and I can remove all my components, all my what do you call instances, like wrap, which is again you can delete or hide, suppress. I will delete it because I want to keep it completely independent. So, and then pipe I keep it, putty I can remove as well, and then I go to the interactions, I keep the step the same, and then the interaction again I don't need these interactions because the components are gone. So now all the other things remain the same. Boundary condition wise also I think these will stay, because yeah, this will stay, this will stay, and also this will stay because these are all fixing or the steel pipe at both ends, and also pressure is internal, so it should stay. And I keep everything the same now, and I run it without any support or composite wrap or putty and see what was the pressure there, and by having this repair, what is the pressure, and then I can suggest any improvements if my pipe repair will be okay, and also what improvements I have got with this kind of repair. So I just go back, mesh remains the same, there is only one part, and you can see it's just that thing. So now I go and run the job. So I just say create, and then I say pipe defect, okay, and then I just press OK, and then I submit. So you can see my system has a limitation of memory, so it's going to take a long time, so I will get back to this. So what you see here is normal pipe, and analysis took a long time to finish, and you can see it failed at around 0.5325 seconds, which is approximately 26.6 megapascals. So this has come out to be the best burst pressure, and you can see without the composite repair, we had a failure at around this pressure, while we were able to increase the pressure, burst pressure to 33 megapascals by using 6 plies. And you can further improve the design by changing the composite wrap thicknesses or number of plies, and you can improve this. I hope this makes sense, and I will see you in the next video. Thank you very much. If you have any questions, then please comment below, and I will try to answer you as much as I can, as I might have missed many things during my explanation. So see you in the next video. Bye for now.